So we already talked about curvature. We did not record a video on it, but I'm still going to make a video because I don't have a video for Hannah. We ended up just doing curvature on the board.
So I can look up online?
It's just a formula, but I'm going to make a video for it.
Okay.
I will make a video.
Should monetize it.
Nash Community College owns it.
Oh, really? You don't want to give them any more money. You already give them enough. So you don't want to.
These are the property of Nash Community College.
Why? Let's go to your face. So you're the property. Anyways.
Is
So-
the account your property, or is this your
And
They own that.
they own her.
So she did her house back.
So we just have half of a section to finish up. And then I've got a few more questions I want you guys to do. It's not as long as the first part. It's got some projectile motion problems and then a curvature problem. And then the last part, which we're going to finish up in 11.9, is tangential and normal components of acceleration. So I know I've already said this a couple times, but one of the things that we can do with acceleration is split it up into two pieces. Every time we do a derivative, derivative describes the change of the previous function. So acceleration is the derivative of what? Velocity, right. So if velocity describes change in position, then acceleration describes change in velocity. Velocity is a vector, which means velocity has two components. It's got speed and direction. So if acceleration is describing the change in that, acceleration is also a vector, and it's got two components. Acceleration is going to describe how speed is changing. It's also going to describe how direction is changing. And we can decompose acceleration into two pieces so that we can see how much of our acceleration is going towards changing our speed and how much of our acceleration is going towards changing our direction. That was a mouthful, wasn't it?
That was.
Sorry.
Open up the numbers.
So we're going to be decomposing our acceleration into two pieces, and it's a tangential and normal component of acceleration. And it helps us decide how much of our acceleration is going towards changing our speed, how much of the acceleration is going towards changing our direction. Yep. Okay? Because we can accelerate in a straight line. That means all of our acceleration is going towards changing our speed. We can be accelerating, but our speed is not changing at all, and that means all of our acceleration is going towards changing our direction. Because acceleration is a vector, and it's got those two components to it, speed or magnitude and direction. And that's just the last little bit in chapter 11 that we haven't talked about yet. All right. There is a specific vector we have not talked about along the same lines as our principal unit tangent vector that we just had on that little take-home. There's something called the principal unit normal vector as well, and that is used in one of our calculations today. So I want to talk about the principal unit normal vector really quickly so that we can go into our acceleration components. All right? Anybody have any questions first? No?
How's your day?
It's been very busy. Very busy.
Thanks.
This whole week is going to be crazy.
Going to be crazy?
There's just tons and tons of meetings. Like Friday used to be the day when I can catch up on things, and I have got meetings back to back to back from 8:45 a.m. until 4 p.m. on Friday.
Wow. That's stupid.
People think if the teachers aren't in class, then they're not doing anything.
Yeah, you don't have lives.
We have already talked about the unit tangent vector. We just did a problem.
R prime T.
So if R of t is our position vector, then our unit tangent vector is r prime of t over
Magnitude.
magnitude. And that's what turns it into the unit tangent vector. So just like back in Calculus 1, we take a derivative to find tangent, but then dividing out the magnitude turns it into unit tangent.
What are we trying to find by curvature?
Curvature? Curvature is a number value that we can assign to a curve to describe how curvy it is.
I'm interested in what kind of application does this have?
What specifically? What do you mean?
Like knowing how curvy something is. Other than like how it like visually looks, it could be applied to like engineering stuff like that, but like if something had like the velocity or something.
If you had, so if all we had was a set of data to model something, and it wasn't something that we can visualize like an electrical field or a magnetic field, and all we had was sorry, physics stuff, I know, sorry. All we had was some sort of machine that could collect data for us, and this isn't something that we could visualize and we could actually see with our eyes what was happening. And maybe we had a machine collecting data for us, and we could model some sort of electrical field or some sort of magnetic field and figure out what sort of direction the energy is flowing in. We can find a spot where there is like a massive shift in the energy by finding the curvature.
We have to do that too.
You may have to one day. You can be an electrical engineer
Nope.
or a computer engineer. So it would be helpful with things that you can't see. And all we have is an equation. We have data, we can create an equation, and we have to be able to figure out what's going on just from the equation because it's stuff that we can't see. Does that make sense? Kind of? Maybe not cool, but with the weather, wind maps are the same idea. We've got all these little weather collecting stations all over America that can collect wind speeds and directions. And you can think of those as vectors because the wind has a magnitude and it has a direction. And if we can come up with some sort of model, we might be able to find tornadoes. If you can find a spot where the curvature all of a sudden is going crazy because it's so high. Remember, curvature is really, really, really large when the circle that fits inside is really, really, really tiny. So that means that the curve is really tight there. So the wind must be whipping around. Just an example of me just making things up. Sounds like it makes sense. This is me just thinking of things that I could possibly do with it.
Why don't you become rich and like figure out how to do it?
I'm sure somebody already has.
Why do we still get destroyed by tornadoes?
It's gotten better. It has gotten better.
What tornado?
It's because people ignore The warnings.
Short
People ignore the warnings
Fake climate is global warming. That's all it is.
because people think global warming is fake.
It is.
Donald Trump told me that.
Gravity's fake too. You see it?
You know, there's a gravity particle. They've discovered a gravity particle.
What do you mean? What does it do?
I thought gravity was opposed to gravity.
Gravity is the bending of space-time. So says Albert Einstein.
Okay, let's keep going.
Fuck gravity particles.
We diverged too much.
I'm recording this,
Oh.
but I could go back. It's my fault. I could go back 10 years in my evaluations, my student evaluations, into the comments. She's a great teacher, but she gets off topic really easily.
I'm gonna put that on you like the How's My Professor website.
She gets off topic really easily. Yes, I know.
Why do you think I showed you that equation earlier?
Okay, so I'm gonna show you some pictures. So if this R of t is our position vector, some curve in space or some curve on the plane, I'm gonna pick a point here and I'm gonna draw the tangent vector. So based on where it connects, I did my best at drawing a tangent. There are technically two vectors that we can draw that would be normal at that spot. What does normal mean?
Parallel? 90 degrees.
90 degrees, perpendicular. Normal means perpendicular, okay? There's three different words, normal, orthogonal, and perpendicular, all mean the same thing, okay? So when we start talking about the normal vector, there's really two options, but there's only one that we're interested in. There's one that's called the principal unit normal vector. And this is the one that's going to help us decide the direction of motion. So if you look ahead in that curve, what direction, if you think of that as a road and a car driving on that road, what direction is that car going to have to start steering, right or left? Left. So our principal unit normal vector is going to point to the right or the left? Left. It's going to point to the left because that is the direction of motion. We want our acceleration to describe the change in velocity. Okay? So it's always going to point into the curve. Our principal unit normal vector will always point into the curve. The one pointing out is also a normal vector, but it's not the principal unit normal vector. So this one here, and they're at a 90-degree angle, this one we're going to call n of t. T of t and n of t are at a 90-degree angle. T is tangent to the curve, and then n is 90 degrees away. There's two options for 90 degrees, but we want the one that follows the direction of motion. And since that curve is going to curve to the left in just a second, we need it pointing to the left or up.
So we're going to find the sign that goes out of the line.
We're not going to have to. We're not going to have to. Nope. Not necessarily. Let me show you the formula. Our principal unit normal vector, n of t, is just t prime of t over the magnitude of t prime of t. That's exactly how we went from r of t to t of t. If you look back up here, to go from r of t to t of t, we did r prime over magnitude of r prime. So it's like r to t to n. It's the same as r to v to a. Position, velocity, acceleration. It's the same idea. So position to tangent vector to normal vector. It's just a progression of derivatives. So to get to your unit tangent vector, do derivative over magnitude. And then to get to your unit normal vector, you take the unit tangent vector, you do derivative over magnitude. T of t and n of t are orthogonal at all points of the curve r of t. They're always going to be at a 90-degree angle. We can. How did we prove it? Back at the beginning of the semester, we were able to prove that two things were at a 90-degree angle.
Something to do with their tangent, right? Something equal 0.
Something equaled 0.
It was the 90.
Something
Was it the inverse? No, it was
What equals 0 at 90 degrees?
sine.
No.
Cosine.
Cosine equals 0 at 90 degrees.
So inverse cosine.
There's something that has cosine in the formula. Something we learned this semester.
Yeah, I remember. It's just like cosine to the negative 1. Cosine to the negative 1.
What's a new operation we learned this semester that could use cosine?
Addition. The new operation? Like addition, subtraction, division.
We didn't learn that.
That's the only operations there are. What's that?
Dot product.
Well, technically, most of us learned that last semester. I'm learning how to see it.
Yes, you learned dot product in physics 1. Dot product. There's two formulas for dot product. There's a geometric formula for dot product that uses cosine. And then there's an algebraic formula that uses the multiply corresponding components and add results. So to say that they are always orthogonal means dot product equals 0. And we said that the principal unit normal vector always points into the curve. So we're going to need this, the t and the n, to help us break apart our acceleration, because acceleration usually is going to be a vector that points somewhere in between them, the t and the n, because the tangent vector is the direction of motion at that instantaneous point in time. So any change there is just changing our speed. And then the normal vector is pulling us away from our direction. So any change there is change in direction. So our acceleration vector is always going to be pointing somewhere in between them, and we're going to decompose it into two vectors that lie on top of our t and our n to figure out how much is in each of those directions, to figure out how much of acceleration goes towards changing our direction, how much goes towards changing our speed. So really, when we do this decomposition, it's really going to just be, what's the word that we did? A projection. We're just doing a projection. We're projecting our acceleration vector onto the tangent vector, and we're projecting our acceleration vector onto the normal vector. But we don't need to know what the entire vector formula is. We already know what the vectors are. We just want to know how long they are. We just want to know how much of acceleration is going to go towards each of those pieces. So acceleration can be broken up into two components. One that changes speed and one that changes direction. These two components are going to be in the exact same direction as t of t and n of t. So this last thing that we're going to be trying to do here in section 9, finally, is going to be taking our acceleration vector, a of t, and breaking it apart into two pieces. The capital T and the capital N, these are just our unit tangent vector and our principal unit normal vector. Those are unit vectors. What we're trying to figure out is how they need to be scaled so that they can be added back together to make the acceleration vector. These two pieces right here, the a sub t and the a sub n, these are the tangential and normal components of acceleration. The a sub t and the a sub n. So you can go around saying a new word today, tangential. Feel awesome. No! You gotta learn something new in here.
What's it mean?
Tangential.
I always thought it was tangential. I never really,
You would, Adam.
I never really looked at it.
Tangential. Tangent to, tangent of.
As long as it's not centrifugal force.
Tangential.
It's not centrifugal force.
Yeah, I'd say it's an adjective. A tangent is a noun, but tangential is an adjective.
What would be the verb?
Tangentialize.
All right. So the A sub T and the A sub N, those are just going to be numbers. All we want to know is how long these are. Okay? We don't need to know the whole vector format for these things. All right? I just want to know my acceleration is this much. How much is going towards speed? How much is going towards direction? I just want to know the magnitude, just how much of each, okay? If you think back to the end of our first chapter, there is something that we did with our projections that helped us. I'm formulating this question very badly already. Where we only used the magnitude of the projection. We only used the magnitude of the projection. We did a projection, but then we didn't care about the vector part of it. We just wanted the magnitude. And we did that for finding distances. When you find the distance between a point and a plane, or the distance from a point to a line. We did it as a projection, but then we didn't care about the entire vector that connected them. We just wanted to know how long it was. We're going to do the same thing here. We don't care about the entire vector that's created. We just want to know how long it is. So this formula is going to look just like the distance formula. And it's going to look just like a piece of the projection formula. Go ahead.
Then we get the distance formula for the vectors at the beginning of the chapter.
We did it at, oh, we're still in chapter 11, right? We split it into two pieces, didn't we?
Yeah, I think.
We're okay, because this is normally, yeah, in my last book, we would have covered 2 full chapters.
Oh, really?
Mm-hmm.
So we're
Yeah,
not
this,
on track?
we're fine.
Okay.
This would have been, this new book
This is
puts
12, pretty much.
this, yeah. In the other book, this would have been
Okay.
the end of the 2nd chapter.
Makes me feel bad.
So here's my acceleration vector. Here's my unit tangent vector. Here is my principal unit normal vector. If I want to project my acceleration vector onto my unit tangent vector, I want the projection of A onto T. I'm gonna write some more. So the tangential component of acceleration, this is just how I need to scale my tangent vector. This is just the coefficient. This is just the magnitude for the projection of my acceleration vector onto my tangent vector. Does anybody remember projection formula?
It's like, it's like in dot V,
Can you use A and T?
A dot T, over
Magnitude of A.
magnitude of A squared, or maybe T squared? Which one is the magnitude of something squared?
Which one do we need to make sure is a unit vector?
I don't remember.
A.
We need to make sure that T is a unit vector. We need to make sure that the one that we're going onto, that its length isn't messing us up. Okay? We need to make sure that the one that we're going onto, its length isn't messing us up.
That one you don't have to multiply T on that side also.
And just a second ago, I said we only want this guy's magnitude. A sub T is a scalar. So we only want the magnitude of that projection. So technically what we're going to do, I'm going to simplify this just a tiny bit. Those magnitude bars are only going to apply to the vector at the end. And they're going to end up canceling one of the magnitude T's in the bottom. And this gives us our distance formula, which is also our scalar projection formula. It's really just A dot T over magnitude of T. A dot T over magnitude of T, which is also the distance formula. What should the magnitude of T be? Should be 1. It's supposed to be a unit vector.
So now we can fix it again.
We could fix it
A
again.
dot T. You say that like you're not sure. Or you really
Well, I just want you guys to think about this and help me a little bit.
Make sure. Just make sure you were sure.
I'm sure.
Okay.
A sub T is A dot T.
This is true.
What do you think A sub N is?
A dot N.
Yes.
Right there. Wow.
So at the end we'll multiply A dot A and A dot T times T plus A dot N times N.
We're not going to do all that. We could do all that to recreate the acceleration vector. All we really want to know is how much of acceleration, just as a number, how much of acceleration is going towards changing position, how much is going towards changing speed, just as a scalar. So like if the magnitude of acceleration is 10. We can say, okay, 8 of that is going towards changing direction. 5.5 of that is going toward changing speed. So it's telling us how to scale t and n to make that little rectangle work. Oops.
On the graph,
Huh?
graph, on the graph.
Can we graph it? Yeah. What are you watching, Adam?
What?
What are you watching?
What?
Spicer?
What?
Spicer?
Oh, no, he spoke earlier. Learn to fly. Two.
Watching a movie?
No. Again. Penguin. Trying to fly.
You're playing a penguin game?
He's destroying an iceberg. Oh, goodness. Okay. Okay, this is not again. Penguin's game. I tried not to make it noticeable.
You try not to make it noticeable.
It's kind of noticeable when I'm sitting here pressing the keys and staring at it. It's fake news, isn't it? Fake. Things like this happen all the time. Keep moving, but drivers off speed.
We want to find the tangential and normal components of acceleration for a particle moving along the position vector. R of t equals, we're just going to keep this an easy one, ti plus t squared j. At t equals 4. Huh? We're going to do a hard one next. We'll just keep it easy for right now, and then we'll do a really hard one. And the one on your handout's impossible.
That's
why I use the calculators. Well, I didn't say.
There is another formula for a sub n that doesn't require you to find the principal unit normal vector. And I did not write it, but it might be worthwhile. And it is V cross A over the magnitude of V. Mm-hmm. Yes.
So is there not one somewhere to be?
Um, no. We can do this because the cross product gives us a normal vector. So make sure that it ends up normal. And then we don't have to go into second derivative with the unit tangent vector, because sometimes that can get nasty. So I guess it all depends on the vector that you start with. Sometimes you can get some pretty crazy quotient rules and chain rules going on here. Because remember, we don't want to plug in t equals 4 until we're done taking derivatives. Another option you have is that these three values should form a right triangle. So you could use the Pythagorean theorem as well. It doesn't look like a right triangle, does it? Sorry. Doesn't look any better. So the magnitude of A is the hypotenuse, and then your A sub t and your A sub n are the two that form the 90-degree angle. So if you get one of them, you can always do Pythagorean theorem to get the other, which somebody was talking about earlier when we were doing talking about projections and stuff. So that's also an option. So there's a way to avoid the second derivatives. If you can get a sub t is pretty easy. There's a way to easily get your a sub n. So let's work on our a sub t first. All right, let's get these examples done. We'll be done. Where do we need to start? We need to find the unit tangent vector, yep. So to get t of t, we need r prime of t over magnitude of r prime of t.
So it'd be 1 I plus 2 1
So r prime is 1i plus 2tj. Magnitude is the square root of 1 plus 4t squared.
We're plugging 4 for 2.
Mm-hmm.
It would be easier just to leave it to the.
We do need to do a dot t. So we can go ahead and do t of 4 right now, and that would be fine. I'm seeing 1 over square root 65. Yeah? Okay. And then, all right, so a sub t is a dot t. So we got the t part. We need the a part. How do we get a?
Yeah, second derivative.
Second derivative, right.
So it's just going to be 2j.
So this was first derivative. Mm-hmm. So here is our t at 4, our unit tangent vector at 4, and then our acceleration vector. We didn't have to plug 4 in there because it didn't have any t values. Okay, if there was still t's in there, we would plug 4 in. And then I just dotted those two. Remember, dot product, you multiply corresponding components and add the results. A only has a j component though, so all we had to do was multiply j components. The I component here is 0, so yeah, 0 times 1 over radical 65 would be 0. So we've got 3 options technically for our a sub n. We can go through our principal unit normal vector, which requires us to do t prime. Look at our t right now. 2t over, we can't do with the 4's in there. 2t over the square root of 1 plus 4t squared. You want to do the derivative of that? It's going to be a quotient rule and a chain rule.
Where are we finding the derivative from? I said find the derivative. Oh,
T of t.
T of T. Oh, okay.
Yep. So we've got 3 options for doing a sub n.
Let's do the V cross A.
We could do v cross a. So we've got our v vector and our a vector. We'd have to do a cross product.
We know what the magnitude of V is anyway.
We could also do Pythagorean theorem. We've just got some radicals we'd have to work with and be really careful about. So it's up to you. I think the least desirable would be doing the quotient rule and product rule stuff. Going through your principal unit normal vector and doing your quotient product rules. Sometimes that T of T ends up really nice and it's not a big deal going through your N of T. But right now that T of T is pretty ugly and the N of T is going to get even uglier. Does that make sense? So there's 3 options to get to your A sub n. And the first option I told you about with the projection is not looking nice. But this one doesn't look too bad. We've already got both of those. We just have to go through the cross product and the magnitudes. And this one's not looking too bad either. If we'd actually write that out, A sub n is going to be the square root of the magnitude of a squared minus a sub t squared. It's just Pythagorean theorem solved for one of the legs. And we should get the same answer either way. Okay? So Adam told me to do cross product. I'm going to do cross product. Since this is a 2-dimensional vector, we're just going to throw zeros in for the k's. Because remember, cross product has the ijk. It's a 3x3 matrix. So just put zeros in for your k's. So we're going to do v cross a over magnitude of v. So for a sub n,
Is that supposed to be in the third dimension? Like, oh yeah, you talked about earlier, I was going to be 90 degrees, okay. Awesome.
what was v? And we can go ahead and plug our 4 in because we're done doing derivatives. Okay, so here was v of t. R prime is the same as v. It's 1i plus 8j, because we're doing this at t equals 4. A of 4, we had highlighted up here, was 0i 2j, and we're going to throw in a 0k.
I had 1, 2, 0, 0, 0, but that's fine, it's subsequent zeros. So you have to plug it in.
For the i's, we get 0 minus 0. So you get 8 times 0, 2 times 0. For the j's, you get 0 times 0. 0 minus 0. You get 1 times 0 and 0, 0. For the k's, you get 2 times 1 and 0 times 8. So you get 2 minus 0. It's been a long time since we did cross products. It's 2k.
That's what I was asking too. That's what she meant by it comes off and goes up.
Yeah, since both of these vectors are in the the xy plane, it makes sense. Remember, the cross product's always going to be perpendicular to them, so it's going to be in just the z plane. We just want the magnitude of this vector. In the top, it's got those magnitude bars around it. We should be able to do that without even doing the magnitude formula, since it's only got one component. Nope. 2, yes. Square root of that thing squared. Square root. The magnitude of 2k is 2. That's the numerator. That's our numerator. In the denominator, we need the magnitude of just our v.
V of 4, right? Or just V? Okay.
Yeah, v of 4, sorry.
So 1 to 60. Okay. There's no T there. Yes.
Is that the exact same thing we got for the other one? No, other one was 16. So a sub t is 16 over radical 65. A sub n is 2 over radical 65. So much more of our acceleration is going towards changing our speed right now than changing our direction. 8 times more is going towards changing our speed than is changing our direction. That tells me, I have no idea what this curve looks like, but that tells me I'm probably not in a spot on this curve where there's a very large amount of curvature. If I'm in a spot where there's a large amount of curvature, then there's probably going to be a lot of my acceleration going towards changing my direction if there's a lot of curvature.
So is that just for that point?
It's just at this, yeah, because we plugged in 4, it's just at that specific point.
You wanted to find it for the whole curve?
If you found it for the whole curve, there would still be, for a lot of them, there would still be t's in the formula. For some of them, like for circles and for springs, there wouldn't be t's in the formula because there is a constant curvature and there is a constant constant acceleration and constant normal and tangent vectors.
Do you remember how you found the magnitude for V cross A again?
Yes. You could just take it and plug it into your, we've got 0i, 0j, 2k.
Where do you get the zeros? Find the zeros for the I and J's.
We break it up into 2 by 2s. So for the I and the j, you're going to do 8, 0, 2, 0, I. And then you do 8 times 0 is 0. 0 times 2 is 0.
I think it's just where you skip that. That's where
Yeah, I started jumping ahead. It's been a long time since we've worked out cross products. At least a week. I'd say it's been a month.
It doesn't take double. It doesn't take quarters. I don't know why. It doesn't want to take. It doesn't want to take quarters.
No, the vending machine for some reason won't take quarters right now.
I don't know if Jim would change it. Huh?
There is a formula in our book as well that links curvature with our normal component of acceleration. So all this stuff is linked together.
No specific spot?
Nope. And then we're all done.
What was that?
That, and then we're all done. Want to find the tangential and normal components of acceleration on the curve r of t equals 10 cosine t, negative 10 sine t, 30 t.
Is this the hard one?
It's really not that hard. But it's 3 dimensions. It works out pretty nice though.
And that's your hand? Or is it your palm? Yeah, or you pick up the car, so you got any friends, so. No, I can do it outside.
So now that you've had a chance to work on this, we'll go over the answer real quick. So for the tangential component, there are some pieces that we need to gather. We need T of t, and we need V of t, because we are going to do, let's see, we're going to do T, nope, and then we need to go from V to A, and we can't get to A without going through V, and then we'll do A dot T. So for T of t, we have to do r prime divided by magnitude of r prime. And then V of t is just r prime. A of t is r double prime. So let me start with r prime here. That's going to be negative 10 sine t, negative 10 cosine t, and 30. Our double prime is going to be negative 10 cosine t, 10 sine t, and 0. And then for magnitude of r prime of t, so we can set up our unit tangent vector, we are going to do the square root of the sum of the squares up here. So that's going to be 100 sine squared t plus 100 cosine squared t plus 900. And if we factor the 100 out, we'll have a trig identity. And this will end up being 100 plus 900. And we get square root of 1,000 for our magnitude of r prime of t. So we've got everything we need for T of t so far. It's going to be our r prime divided by our magnitude of r prime. 1,000 is not a perfect square, but we could simplify this down to 10 root 10 because our r prime has some 10 coefficients in it that can cancel. So if we do r prime divided by magnitude of r prime, all those 10s will cancel out. We end up with negative sine t over radical 10, negative cosine t over radical 10, and then 3 over radical 10. And we want to dot this T of t with V of t to get our A of t. So A sub t, nope, I'm sorry, I've said that twice now. We want to dot it with A. A sub t is A dot t. A sub t is A dot t. So with the dot product, we multiply corresponding components and add the results. So I'm going to multiply my I components together. And that's going to end up being positive sine t cosine t over radical 10. Multiply your j components together. That's going to be a negative sine t cosine t over radical 10. And then multiply your k components together. And that is going to be plus 0. And these two terms are exact opposite. And then plus 0, we get 0. So a sub t is just 0. So if we're trying to break our acceleration down into a tangential and normal component, there is nothing in the tangent direction. What that means is that none of our acceleration is going towards changing our speed. This object is moving at a constant speed. It is not accelerating or decelerating. It is moving at a constant speed. All of the acceleration is going towards changing direction. So probably the easiest way to get a sub n is just with the Pythagorean identity, because we are taking our acceleration and we are breaking it apart into these orthogonal components, a sub t and a sub n. So a sub n, which is just one of the legs of that right triangle, is going to be the square root of the magnitude of our acceleration squared minus a sub t squared, and we just found out a sub t is 0. So a sub n is just the square root of the magnitude of a squared, and here I'm taking the square root of a square. That means a sub n is just the magnitude of acceleration. All of our acceleration is in the normal component. All of our acceleration is going towards changing direction, and that is because none of it is tangent to the curve. None of it is going towards changing our speed. So to get the normal component, all we have to do is go back to our acceleration vector and figure out magnitude. So the magnitude of our acceleration vector is going to be 100 cosine squared plus 100 sine squared plus 0. And if you factor your 100 out, sine squared plus cosine squared is equal to 1. This is just the square root of 100, which is 10. So the magnitude of our acceleration is 10. All of that magnitude is in our normal component. None of that we found was in our tangential component. This curve, if you were to graph it, in the xy plane, we've got a circle of radius 10. It's starting on the x-axis, but because the y component is a negative 10, that's going to have us moving clockwise. The z component is 30t, and that's going to have us moving really quickly up the z-axis. So if you look at this graph, it's going to start out 10 units on our x-axis, and it's going to move up very fast. And as an object moves up this spiral with a radius of 10, it is moving with a constant speed. And the only acceleration it's experiencing is that constant curving along the circle. That constant curving along that circle of radius 10 is the only acceleration that it's experiencing. No speeding up or slowing down whatsoever.